Chapter 2, Motion in One Dimension. So from this chapter, we're going to formally start our study of classical mechanics. Now, before I get on to any details in Chapter 2, let's have an overview of how Physics 8a is divided. How do we put different parts of classical mechanics together? As you know, Chapter 1 is not exclusively about mechanics, it's about unit systems that applies to every branch of physics. And Chapter 2 and Chapter 4 will be dedicated to what's called particle kinematics. Okay, and then you say, what about Chapter 3? Well, Chapter 3 is a mathematical prelude to Chapter 4. It is about vectors. It's because in Chapter 2, we focus on one-dimensional motion, which does not need any vectors. But in Chapter 4, we're going to go beyond one dimension to 2 and 3 dimensions, and that's when vectors become necessary. That's why we put vectors as mathematical preparation in Chapter 3 ahead of Chapter 4. And then starting from Chapter 5, ending at Chapter 9, we're going to study what's called particle dynamics. And then Chapter 10 through Chapter 12 will be rigid body mechanics. And after that, we'll get into special topics of mechanics, such as Chapter 13 will be about universal gravitation, and Chapter 14 is about fluid mechanics. So if you look at Chapters 2 through 12, these are the foundations of classical mechanics. But let's see how we divide these chapters up in terms of the content. All right. First of all, there's a concept called particle here. Particle. And there's also a concept called kinematics versus dynamics. So what's a particle? We're going to talk about in a minute. But let's first talk about kinematics versus dynamics. Okay, kinematics and dynamics are both branches of mechanics, but they answer different questions at different depths. Kinematics deals with the questions of how. How do things move? You know, mechanics is about the study of motion, right? How do things move? The questions of how. That's kinematics. You describe motion, right? You want to know where the thing is. You want to know how fast it moves. You want to know whether it speeds up, it slows down, whether it made a turn, that sort of thing. It describes the motion, but it doesn't address the reasons behind motion. That will be the subject of dynamics, the questions of why. So that's the difference between kinematics and dynamics. And with kinematics, the questions of how. And that will be done in chapters 2 through 4. And then in chapter 5, we'll be introducing particle dynamics, especially chapter 5. The very first chapter of particle dynamics is the most important chapter in Physics 8a, because this is the chapter in which we introduce the fundamental laws of particle dynamics, known as Newton's 3 laws of motion. Right? That's in chapter 5. And starting from chapter 10, we're going to go away from particles and get into what's called rigid body. I want to talk a little bit about the difference between particles and rigid body. But the whole idea is we're going to start from something simple. Okay, we're going to start from something simple and gradually get into something more complicated. And to see how that works, let's see what a particle really is. Now, this word particle in the current context is a simplification of the real world in the sense that we're looking at something with only position, but no shape and no size. All right. Now remember, there's no such a thing as only a point with no shape and no size. Everything, no matter how big or how small, has a certain shape, has a certain size, right? But here is a simplification of the real world called a particle. We do not consider any shape, any size. Think of it as a point. This thing doesn't exist in the real world, and yet, can we get away with it? Well, it turns out the answer could be yes, depending on the circumstance. Einstein famously said, everything should be made as simple as possible, but not simpler. What does that mean? It means that when we do physics, we try to find a theory to describe the natural world, and the actual world is very complicated and a lot of details, right? A lot of features, a lot of details. And our job is to simplify our description of the real world to a point where it becomes mathematically feasible to perceive. if you retain all the details, you find quickly enough, you find that the problem simply becomes mathematically impossible to solve. So we have to simplify it. But when you simplify it, you're allowed to do that as long as you do not lose the essential features. Because if you keep on simplifying, at some point you're going to go into something wrong because you will oversimplify, you will lose the essential feature. And that is why Einstein said everything should be made as simple as possible, but not simpler. And to this end, let me introduce a concept called model. Okay, this word model in science means it's a simplified version of the reality. Again, we need to simplify it because that's how we can deal with it mathematically. It becomes possible to do that. So it's a simplified version of the real world. It's not 100% accurate, but it does retain the essential features of the real world. And hopefully this will be enough to describe the problem that you want to deal with. I use this analogy to show you how that works. Here's a picture of Einstein. Right? So you take a photograph of Einstein, you see all the details, and if the photograph has enough resolution, you can even see every strand of hair, right? And there's no omission, there's no compromise when you take this photograph. Everything is in all the details. But then if a person want to recreate this photograph by drawing, it's going to take that person a long time. You have to be specially trained. It takes a lot of effort, a lot of time to do something like that. And when that is not possible, you compromise. Okay, so what you say is, okay, let me draw a picture that is somewhat simplified. So you go from here to there, somewhat simplified. So you see a picture like this, but this picture still has a lot of details, even though it's not as hard to draw as the first one, as the photo reproduction of Einstein. So it's slightly easier. Okay, so you can see the details. Right? It's slightly easier, but still there's a lot of work you have to do. So if you think of this as a model, you think of this as a model of the real Einstein picture. This model has some simplifications, but if you're still not able to deal with that, you can simplify it still further. You can draw a cartoon picture like this. Okay, you can draw a cartoon picture like this, and this is much easier to draw. But everybody can still recognize that this is Einstein. Why? Because it retains its essential features, right? You have this famous Einstein hair, right, that sticks out everywhere. You have his big nose. You have his tongue sticking out. It's actually a famous pose made by Einstein. So even though this is a much more simplified version of the realistic picture, it still retains its essential feature. So you can still recognize that this is Einstein. And you can even go further. If you don't want to draw something like this, you can go even further. You can go like this. That's an even simpler version of the cartoon picture of Einstein. So all these are models at different levels of complexity. Okay, they're all valid if you want to find essential feature of the person. They're all valid because they can all be for you to recognize the person being drawn, which is Einstein. Okay, and they have different level of complexity depending on what the purpose of a drawing is. And in physics, that's what we do. We take the real world and we try to simplify it by neglecting the non-essential features and keeping only what's important, right? To a point where it becomes possible to do that. And particle is just one such example. A particle. Again, what's a particle in this context? A particle is a model of the real world object. We simplify it to a point. That is, we ignore the shape and size of the object. We think of it as a point. Again, we can do that in some context because the shape and size are not very important. Example, the Earth. Can you think the Earth as a point? Well, the answer to that depends on the context of the problem, right? I mean, if you're looking at, if you're a geologist, you want to study the Earth, can you think of the Earth as a point? No, there's no point studying a point. You see what I mean? Okay, you have to look at the entire Earth as made of different continents and different parts and so on. You're studying the details, you're studying the features. You cannot think of it as a point. Certainly not, right? But if you look at a different problem involving the Earth, look at the Earth and the Sun. You ask yourself this question: the Earth moving around the Sun. Here's the Earth, a tiny little dot here. okay, a tiny little dot here, the Earth, and here's the sun. How long does it take for the Earth to go around the sun? That is a year, right? How do you figure that out? It turns out you can do so when you apply Newton's law of universal gravitation, we studied in chapter 13. And in doing so, we can safely ignore the size of the Earth. Because why? Because the size of the Earth, the radius of the Earth is far less than what? The distance between the Earth and the sun. Okay, far less than, here's the Earth to sun distance from here to there. It is far longer than the size of the Earth. So in this context, we can think of the Earth as a point because the size of the Earth makes very little difference to the answer, which is the length of a year. Similarly, you can think of you driving to PCC from your house, right? If I ask you, oh, how long did it take for you to drive from PC to the house or from house to PCC? And you say, oh, half an hour. Now, when you answer this question, do you think the size of your car make a difference? Not really. You can think of a car as a point, right? At the point. So that's another example. So it depends on the context. In some contexts, you can ignore the shape and size because of the relevant size of the problem. Okay, but sometimes you cannot. You know, look at this. Look at this picture. Here's a photo. Here's a photograph of Usain Bolt leading everybody else in a 100-meter dash. Let's say here's the line, right? Here's the line. Here's the finish line. He finishes first. In fact, whichever part of his body triggers a photo sensor connecting pass through this line, he's considered done. He's considered there. So you know, it really makes a difference. You know, whether his forehead passes the line first or with one of his feet passes the line first. It makes a difference. You cannot think of Usain Bolt, the person, as a point, even though you can the entire Earth as a point in a totally different problem. Okay, so it's a relative thing. It depends on what you're looking for. And we can also think of things as a point if the shape and size do not change the outcome. Consider this problem. Here you have a tire, okay, rolling down an incline. Now, if I replace the tire with something else, or replace with a football, okay, I should replace with a soccer ball with circular cross section, or replace with a Coke can. Does it make a difference if I raise a Coke can versus a soccer ball? Raise them down the incline. Will they reach the bottom at the same time? It turns out they don't. Even if you raise, you know, two identical-looking eggs, one is boiled, hard-boiled, the other is the other is raw. They're not going to reach the bottom at the same time. Okay, so can you think of the Coke can and the soccer ball as a point? No, because the shape and size made a difference. That's why they arrive at the bottom at different moments, right? So it's not, you know, the Earth is big, therefore I cannot think of it as a point, and the soccer ball is small, I can think of it as a point. No, it depends on what you're looking for. Okay? So sometimes we can think of something as a point, sometimes we cannot. And in some cases, you have an object which is actually pretty big, and yet the way it moves is such that every point on that object moves the exact same way. Think of this example. You have a car being driven on level horizontal road in a straight line, right? This entire car, there are different parts, is obviously not a particle, but if you look at any point, say this point, okay? This point went from here to there. It went through a certain displacement. Now look at another point. Another point, say here, this point, the corner of this monitor went from here to there. Or if you look at yet another point, this point right here, it went from here to there. All these 3 points went by the exact same amount, moved by the same amount. As long as the car doesn't flip or doesn't make a turn, you know, straight line, that's what happens. So you can think of any point on that entire car as a representative point because the motion of any other point is just the same. Okay, but on the other hand, if the car makes a turn, then it's going to make a difference. You know, different part of the car will do things differently. So the same object, depending on how it moves, sometimes can be treated as a particle, sometimes cannot. Okay, now at this point, from chapter 2 all the way through chapter 9, we are going to think of our object in question as a particle. That is, we're going to only look at a situation where the object can be simplified as a particle, because obviously it's easier to study than an object with shape and size. Okay, that's, we're following what Einstein said. Everything should be made as simple as possible, so we can simplify it as a point, as a particle, to the extent that we can. Sometimes it turns out we cannot do that, and then when that happens, this Coke can versus the soccer ball, we cannot get away with that. Then we have to consider the shape and size. And even with that, even under that circumstance, we still want to ask ourselves, can we simplify the situation? Well, you still can. If you look at the soccer ball, look at the Coke can, strictly speaking, they're deformable objects, right? They're not 100% rigid. But do you want to study a object whose form and shape and form can deform? No, you don't want to, unless you don't have a choice, right? So if we have a situation where the shape and size of the object cannot be ignored, then we cannot think of it as a point particle anymore, but we would rather study what's called a rigid object. It's an object with finite shape and size, but the shape and size do not change. That's why we call it a rigid object. Okay, of course, there are objects that are non-rigid, but we're going to start with rigid object. This is the reason why we study rigid body mechanics after we study particles. Okay, so for the first a few chapters, chapter 2 through 9, we will focus only on particles. We ignore the shape and size of the object when possible, and when that becomes impossible, we go to the next best thing, that is we're going to study a rigid body, right? And that is chapter 10 through 12. So that's how we divide the first 12 chapters. After that, like I said, it's all going to be specific topics covering a certain type of mechanics, such as fluid mechanics, such as gravity, and so on, starting from chapter 13. Okay, so that is how we divide things up, and that is the reason why we're going to start with chapter 2, one-dimensional particle kinematics. And the title is called motion in one dimension, but a more proper title, I would call it, again, one-dimensional particle kinematics. So we study kinematics, we only describe the motion, and we study kinematics of particles because they're easiest to study, and we can restrict motion in one dimension. Now, it goes without saying that one dimension is easier to study than 2 and 3 dimensions, because in one dimension, okay, here's a line on which the object is moving. It cannot possibly leave that line. Why is it easier? Because in one dimension, everything can either move this way or that way. There is no third possibility. And there are therefore only 2 directions possible. And we call one of them positive, the other one negative. That's all we need to do when it comes to telling the directions apart. With 2 choices only, we call one positive direction or negative direction. So the 2 signs, positive and negative sign, will take care of any possible directions in one-dimensional motion. There is no need to introduce vectors. It's not necessary. That is not until chapter 4, when we move beyond one dimension, when vectors becomes necessary. Okay, so we're going to focus on one-dimensional motion of a particle. We study its kinematics, and that is the subject of chapter 2. So starting from the next lecture, we'll get into the details of how do we study the one-dimensional kinematics of a particle. What kind of questions we'll be asking, what kind of solutions we'll be getting.